Hello and welcome to Behind the Scenes, where we take a closer look and a deeper dive into our course material. I hope everyone's doing well out there in my DiffEQ crew. I want to talk a little bit about the Laplace transform. So we've been talking about this in lecture quite a bit. We'd say the Laplace transform of some function, f of t, is defined as the following improper integral. We have the integral from 0 to infinity of e to the minus st times f of t dt, and that this gives us out some function, capital F, of variable s. And remember what's going to happen here. We're integrating with respect to t, so we get some antiderivative, and then we plug in the upper bound and the lower bound, replacing t. And in this case, we need a limit because we can't plug in infinity, we can't treat it like a number. But so all that really leaves us with is this variable s. So we do get a function of s out of this. And, depending on what your studies bring you to, I think that if you're doing engineering or physics or anything like that, then you're likely going to get a lot of experience with the Laplace transform and thinking a lot about it in terms of applications. And you're going to think about it as moving from some time domain t into some complex phase space s, and all sorts of interesting applications from there. However, being that we're discussing sort of the mathematics behind these things, I want to give you a little bit more intuition and some ideas that you can sort of take with you to try to connect the Laplace transform to things that you've already learned about in Calc 2. Now, before I get too ahead of myself, I just want to mention that this isn't stuff that I necessarily came up with entirely on my own. This actually comes from a great lecture by Arthur Maddock, and if you have a chance to check him out, he goes into a little bit more detail than I'm going to now. But I want to bring you back to a comfortable, safe space. I want to bring you back to Calc 2 when you were talking about sequences and series. And in particular, I want to talk about those infinite series again. So we would have some sum from n equals 0 to infinity. And we would have our power terms, x to the n, and we would have some coefficient to the series, c sub n. And we were very interested in these infinite series. We wanted to know when do they converge, under what conditions, and what do they converge to. Now, another way that we can write this, and it's going to be helpful for us to do this, is not writing the coefficient as c sub n, but rather using a bit of a functional notation. So it's really going to be the same thing still, just making a slight change to it, but it's not going to mean anything different. Instead of calling it c sub n, we would say c of n, meaning I'm going to plug n in, and then I'm going to spit out some coefficient. It doesn't really matter how you call these, but just to get an idea as to what's going to happen here, I think it's better to think of this c sub n instead as a function of n, where we're going to plug in the n values starting from 0, moving by integers, on and on, and we're going to get some coefficient then to the power term that coincides with that. And we want to know, what is this equal to, right? What does it give us? Well, that's sort of a loaded question because these things don't always converge. However, if it does converge, then it's going to give us some function of x. And depending on what we have for that coefficient, our c of n, we might get something that converges, we might not get something that converges. And there's a few of these that you would have seen back in Calc 2, and we even talk about them a little bit in our lecture too, back with our series solutions. If we have that c of n is equal to 1, then we do get a function out of this. The function that we would get for f of x is 1 over 1 minus x. And that comes with a restriction that would mean that x has to be between -1 and 1. And this is a very popular series. If c of n is just 1, then we're really just talking about the sum from n equals 0 to infinity of x to the n, which gives us this interesting sort of geometric series type result. And of course, there are others. You can probably think of a bunch, but I'm just going to talk about one more very common one, is that if c of n is this 1 over n factorial, then we get everyone's favorite function out. We get the exponential function base e to the x. And this is true for all x. So there's actually no restriction that needs to be made on this one, as opposed to this previous one. We had to say, well, hold on. The sum of x to the n doesn't always converge. It converges when the absolute value of x is less than 1, with the radius of 1, right? But e to the x, that's for all x, so there's no restriction there. And this would be the popular series, the sum from n equals 0 to infinity of x to the n divided by n factorial. Gives us that e to the x. Okay, so, I mean, that all sounds great. But let's go ahead and talk about this a bit further. What I want to mention about the series that we have here is that they're discrete, meaning they don't run a continuous interval. They stop at integer values. So n is 0, and then a big gap, and then n is 1, and then another gap, and then n is 2, n is 3, n is 4. But we're missing all of those values in between. So this would be a discrete case. And we would say instead of a discrete case, consider a continuous version of this. And there are some changes that we would have to make. So here when we're talking about working with a series, we would say, okay, so now we're talking about these discrete values, n is 0, n is 1, n is 2, n is 3, so on and so forth. That's not continuous. So instead of working with these discrete values, I want to work with an interval. We'd say, well, let's consider, instead of going 0, 1, 2, 3, 4, so on and so forth, let's consider the interval from 0 to infinity. And this will be an interval on a variable. I shouldn't use the same variable n, since that has sort of a connotation with it that it's going to be discrete. So instead we use a continuous variable like t. So we'd say t exists in this interval from 0 to infinity. And if you haven't seen that sort of set theory notation that I guess I'm not even doing a great job representing it either, you could just say, well, this means that we have t in this interval from 0 to infinity, is what we're sort of thinking about. So we got our continuous variable now. No more of that jumping around at 0, 1, 2, 3. Now we have a continuous interval starting at 0, going all the way to positive infinity. What else do we want? Well, from there, we'd say, I don't want to be summing, right? If I'm going to be adding things up to infinity, I mean, that's fine in the discrete case, but if I'm continuous, we're not going to do that. Instead, what takes place of the capital sigma notation, this summation symbol, is the integral, right? So we'd say, well, let's go ahead and change this. We're going to integrate now. We're going to integrate from 0 to infinity. So we get our integral. And we want to change this a bit more. So if we remember what we were saying back at the beginning, we have some function of n, and then x to the n. That's what we're thinking about. But now I want to make those sort of changes. We're saying instead of n, we have t. So let's call this a function of t, and then it should be x to the t. I could call it c of t, but let's just change it to f. We'll say little f of t, and then x to the t dt. Okay, so pretty good. So t is going to take on these values from 0 onward to infinity. All of the values are going to be there in the interval. We have this integration that we're considering, and we want to know, what does this give us? Okay, well, not exactly an easy question to answer right away, but there are a few things that we can mention. First of all, I want you to notice that t is going to be, going from 0 to infinity, but that in order for this to converge, to give us something nice to work with, we have to put some restriction on x. Or we'd say, well, what do we expect of x then if we're hoping for this to converge? If it diverges, we don't get anything useful anyways, so we're only really interested in convergence here. We'd say, okay, well, x then, if I'm really thinking about it for a bit, x should be positive, but I want x to be positive. Because let's say, what if x was negative? If if I had some negative number for x, then depending on what t is, I could be talking about complex numbers, which isn't something that we want to do in this case. Let's say that x was something like -3 and that t happens to be 1/2. Well, -3 to the 1/2 power is not real anymore, and we got an issue there. So we'd say, well, let's avoid that. Let's make sure that x is positive. But then on the other side, we'd say, well, if I still want it to converge, I want to make sure that x is small enough so that this will give me some convergence. And we'd say, well, if x is larger than 1, let's say x was 2, for example, then as t gets bigger and bigger, that's going to blow up. It's going to diverge, right? You'd say, I have this continuous interval, but you could think, 2 to powers, or 3 to some power, or 4 to some power. As those exponents get bigger and bigger and bigger, heading to infinity, it's going to diverge. It's going to get larger. So we'd say we really don't have a lot that we can work with in terms of x. It should be positive, and it should be less than 1. So we have some restrictions to work with here. We're saying, okay, x, we need x to sort of help us out a bit. If this is going to converge and give us a useful result, we need x to be between 0 and 1. Okay, so that looks good. We're still not quite there, though. So the next thing we want to talk about is something that's really just going to help us integrate. I want to make this easier to integrate. We'd say integrating something like x to the power of t doesn't really seem like it's going to be an easy task, right? So we'd say we want to rewrite x to the t so that it's not just base x. In fact, the easiest thing for us to deal with in calculus in most cases would be if I had something of base e, right? That exponential function. So if I have to integrate or do some type of calculus, I don't want to leave this as x to the power of t. I would prefer something with base e. And we can rewrite this if you remember that x is the same as e to the natural log of x. We could go ahead and say that x to the power of t is the same as e to the natural log of x to the power of t. And then since this is re-raising, these just multiply. The exponents would just multiply. We would say e to the natural log of x times t power. And this is really the same thing. So we're going to make this replacement. Then, and we're going to say this is the integral from 0 to infinity of f of t times, instead of x to the t, we're going to have e to the natural log of x times t power dt. But there's a bit more that we can talk about with this. There always is, right? If x is between 0 and 1, then what can we say about natural log of x? If you think about how the natural log function looks, or if you think about values of it, when we have natural log of 1, it gives us 0. And when we have natural log of 0, it is undefined. So if I'm in between those, say, well, natural log, let me get a different color here. Don't want to do too much with the pink. If you like green, we all like green. We said natural log at 1 is 0. And then we have that slow logarithmic growth. But as I get closer to 0, but less than 1, we have these negative values. So something like this, right? So we'd say if x is between 0 and 1, then natural log of x is negative. And that's important information, that this ln of x always takes on a negative value. So much so that we want to showcase that. We don't want anyone to be sort of thinking, well, ln of x could be anything. Well, no, in this case, in order for us to have any hope of convergence, we need the restriction that x is between 0 and 1, which then it follows from that natural log of x will have to be negative. I need ln of x to be negative. So we could go ahead and make another substitution still. We would get another dummy variable to work with. We would say replace natural log of x with negative s, where here we can regard s as being the absolute value of ln of x. since it's going to be negative, we would say, well, let's put that minus sign right there so everyone's staring at it can say, okay, it's negative, and then s is just whatever the magnitude of that number is. Let's put all these things together. We have the integral from 0 to infinity of f of t times e to the ln of x times t power, but we said let's replace ln of x with negative s because it's always going to be negative, and I want the reader, whoever's talking to me about it, knows that it's always going to be negative. So e to the minus st dt. And hopefully this looks familiar. This is our Laplace transform, right? And we would say I'm going to integrate with respect to t. I'm going to go ahead and evaluate this, and this is going to give me out some final result, some function. We'd say, well, it's going to be a function of what variable then? I'm going to integrate with respect to t. T kind of feels like the star of the show, but then I'm going to evaluate. I'm going to take a look at my limit as t goes to infinity, and then subtract away what happens when t is 0. So all that's going to be left in terms of some variable of the function is going to be s, right? So it's going to have to be a function of s. So I get this function, big F of s. We could go here and say, similarly, with this old sort of working definition I had, we'd integrate with respect to t, and we'd plug in for t the upper and lower bounds. So this would have given us some function of x. But then we went and we made some replacements, and then at some point here, we replaced the mention of variable x with s. And so this sort of hopefully gives you an idea as to where the Laplace transform comes from. I think it's best, and certainly less menacing, to think of it as just this continuous version of what we were doing with our series back in Calc 2. We'd say, well, if I want to think about this not in a discrete case, but in a continuous case, I'm going to make these replacements. I'm going to make some of these sort of smaller replacements that serve as luxuries for ease of computation to make it look a little bit nicer, of course. But we see that all this really sort of does is it builds on something that we already talked about in a previous semester. But I hope this sort of helps this gives you an idea as to where the Laplace transform comes from and why we're so interested in it in terms of mathematics and where it sort of comes from with that bit of a background. And there's tons of applications for this. If you're an engineering major or a physics major, you've probably already seen and worked with it, but hopefully this gives you something a little bit interesting and a little bit different to consider when you think about the Laplace transform and where it comes from. Hey, thank you so much for watching. Me and my stylus are out of here. But look, you need anything, you know where to find me. I hope you're having a great day. I hope you have a great rest of your day. I hope if it's at the end of the day that your entire day was great. But I will see you soon. All right, take care.